Yeah, welcome everybody to the this special TUT seminar. Thank you for coming. It's a pleasure to welcome Tutte-Niv Buchbinder. So Niv is a professor in Tel Aviv in statistics and operations research. And he did his PhD in 2008 at Technion. And after that with Sefi now. And after that he moved on to Microsoft Research in New England for a postdoc for 2 years, and after that then Tel Aviv. So it's Niv's area of research is, so his PhD thesis was on online algorithms, in particular primal dual framework for online optimization, very well known, and today he's here to talk about some new results that he has together with Moran Feldman on deterministic algorithms, faster algorithms for submodular maximization subject to Matroid constraints.
Yes. Thanks a lot for inviting me. So I'll explain all these words, and so don't worry. Everything should be really simple, and you are welcome to ask easy questions that I know how to answer. So this talk is based on two joint work with Moran Feldman from University of Haifa, but also I will explain some other things that were done in this area of submodular maximization. So I will start with the motivation of this talk, which is I'm going to tell you how to select the best meal or algorithms that will give you guarantee to select the best meal. And the first question that you should ask is, here you have one meal, and here you have a slightly larger meal that contains more dishes. And I ask you, what is the added value of a dessert to each of these meals, and where is the added value it adds more, right? So the right answer here, there is only one right answer here right now, is that this smaller meal, the added value is more because here, for example, you have already a dessert. So the added value, the dessert worth more to meal one, which is kind of smaller than to meal two. And this is called diminishing return. And this motivates the main definition of this talk, which is a submodular function. So we have a ground set, n, which is just dishes element, or dishes. And then we have a submodular function. Here it will be non-negative. In general, it can be negative. And it has the property of diminishing marginal returns. So what does it mean? So I drew it for here on the board so you can remember. So when you have a subset of dishes and another subset of dishes that contain this subset, and you take another element that is outside of these two sets, then the added value to set A is more than the added value to set B. So I'm usually saying that the added value of U to the larger set is less than to the smaller set, but smaller and larger means actually containment. Okay, so this is the drawing that you should have in mind, and this is the marking of the marginal contribution or the added value of element U to subset A. So this is my definition of submodular. The usual definition is just that for any two sets S and T, f of S plus f of T is more than the function on the union and the function on the intersection. But these two are equivalent, and I really like this, which is more intuitive. So I will use this definition. Great, so this is the definition, and you can all recall this definition on the board. So now, how do you access these submodular functions? So these are set functions, so there are 2 to the n subsets, and you don't want to look at all subsets on the value. So there are several ways of accessing, black box accessing of a submodular function, and the simplest one that we are using here is called value oracle. So it just says that I give you a subset of dishes, and you tell me exactly how much it's worth for you. how much is the value of this subset. This is a value oracle, and the only access that we will have in this talk to the function is via this value oracle. Another property that I call additional dessert never hurts, which is not always true, and we will see in this talk that it's not always true, is called monotonicity. And this means that if you add more and more elements, it will not hurt you. It will only increase or never decrease the value of the function. So as you know, and we will see it's not always true, but at the beginning of the talk, we will talk about monotone submodular functions. Great. I'm really like to speak about choosing dishes in meals, but I heard people here like combinatorics. So let me give you two more prime examples of submodular functions from combinatorics that you can think about during the talk. So one is coverage functions. So coverage function, we have a set cover instance. So these are the sets, and I didn't draw the elements that are inside these sets, or you can think about the area that they cover. And now it's a bit confusing. The element of the submodular function are actually the sets that you choose. And then for any family of sets, these are the elements, the function is just the area or the number of elements that are covered. And it's easy to see that this is a monotone function because adding more sets will cover more area. And if you add a set to a family, a larger family of subsets, it will cover, the marginal area that it will cover will be smaller. So it's easy to see that this is a monotone submodular function. What is a non-monotone submodular function? So prime example are cut functions. So you can think about a graph, directed, undirected, capacited, or without capacities. And then the function is just you take a subset of the vertices and you measure the capacity that cross the cut. Capacity or number of edges or anything like this. And it's an exercise to see that this is a submodular function, but it's non-monotone because if you add an element, the cut may shrink. So this is an example of a non-monotone submodular function. Okay. So what can you do with a submodular function? You can either minimize them or maximize them. Maximizing is much more fun, so here we are only doing maximization. So the main problem here is that you are giving a family of feasible subsets, and then you should find a feasible subset that maximizes the function on this subset. And there are lots of interesting families. So even unconstraint is interesting. Unconstraint is you can choose any subset of elements. So if the function is monotone, choose everything. But if the function is non-monotone, this already generalizes max cut or max directed cut. So this is an interesting question. Another natural family is just you can choose k dishes, at most k dishes. So this is interesting both in monotone and non-monotone. It will give you max coverage, for example, if you know the problem, or max cut with some specified imbalance. There are Matroid constraints that I will explain in a minute, but you don't need to know a lot about Matroids. But you can think about any family of feasible subset, any packing, knapsack, your favorite feasible subset. Great, so what is in the area? So as I said, there are various constraints, family of feasible subset. There are monotone, non-monotone submodular functions. There are more definitions that capture other properties of the function. There are deterministic and randomized algorithms. And basically, the basic question is, what is the best approximation that we can get, and at what time? Or even here in a cleaner way, I will just measure the query complexity of how many sets I should query in order to get this approximation. This generally dominates the running time of the algorithms. So this is the basic question, and then you can ask this question in other models and have your favorite model. So people around here work on streaming, for example. You scan the elements and you have bounded memory. Online or dynamic environment where elements arrive, depart, and you want to maintain a good solution. Random arrival, secretary type, parallel, distributed, so any model. So plenty of questions here and plenty of research that is interesting. This is very active field. Again, the basic is just what is the approximation that you can have. Great. So I will tell you briefly about Matroid, just because our result works for any Matroid, and then I will say in a minute that you don't need to know anything about Matroids for this talk. So all our results work on Matroids. You should think about linear algebra with vectors. All the notation comes from this thing. So the feasible subsets are called independent sets, the feasible subsets. And there are two properties. One is down-closed. It means that if a subset is independent and you remove elements, it remains feasible independent. And the other, this is the interesting fact, if you have two independent sets and one is larger than the other, you can always find one element from the larger set to add to the smaller one, and it will remain independent. So these are Matroids that I will say you don't need to know a lot, but I will use the rank, or the letter R here in the talk, which is the maximal size of an independent set. This is the rank, and a base is just a maximal independent set. When you speak about general Matroids, you also need some access to see what groups are, what subsets are independent. So we use the simplest one, which is called the independence oracle. You just give me a subset, and then I will tell you whether it is independent or not. This is called independent oracle, and I use independence oracle and rank. But here you don't need to know about general Matroids. I will speak only on maybe uniform Matroid, which is how to find the best meal that contains at most k dishes. Or the other, this is the interesting, is called partition Matroid, or simple partition, where you want to find a balanced meal. So what is a balanced meal? You can choose at most one main course, one side, one glass of wine, one dessert, and so on. So from the menu, you want to pick one dish from every part. So this is mostly I will talk about partition, but everything that I say will work for general Matroids with some trivial generalization. Okay. Everything is okay? Great. So first, let's start with the simpler case, which is when the submodular function is monotone and we want to maximize it, subject to Matroid constraints, but think about partition. So what was known about this problem? So this was a breakthrough result that gave a randomized algorithm that is 1 minus 1 over E approximation. So you should read it, the 0.63 means that you actually get a meal that is at least 63% of the optimal meal that you can get. And this is known for a long time to be optimal. So this is optimal both in NP hardness and both in information theoretic if you just have access via value oracle. So this 1 minus 1 over E is just the optimal that you can get. Oh, it's telling you. But what about deterministic algorithms? So deterministic algorithm, it is known that greedy, and I will tell you about another algorithm, is half approximation. But nothing better was known except one result that we had several years ago that gave slightly above this half approximation. And the question is whether you need randomization to achieve this 1 minus 1 over E. And this is not just complexity. You have access only with a value oracle. And what we showed is that you don't need randomization. So what we showed is that you can get a deterministic algorithm, which gives you 1 minus 1 over e minus epsilon, with something that the query complexity that you need is something like quadratic. So here you should think about R as large, but not too large. So think about R as something like square root of n. So this O tilde also hides some logarithmic terms and some dependency on epsilon that I will discuss at the end. So you can get deterministic algorithm, and actually we even got a randomized algorithm, which is faster than what was known before, slightly faster. It's almost linear, especially if R is small. And the nice thing is that the algorithm is really simple. I will just tell you what is the algorithm, except for some small cheating. So let me tell you what is the algorithm. I will not prove, but the proof is actually like 2.5 pages, not more. So the first building block that I need is local search, which is the most obvious algorithm that you can think about. What is local search? Just switch an element, switch a dish whenever it benefits you. So let's talk about partition Matroid. So here is the notation. You have a basket here. You have a main course, a side, a glass of wine, and everything. These are all the main courses. And then you can select one dish, at most one dish. So you chose U1, U2, U3 from each of the R partitions. Okay, and then what is local search here? So local search in a partition Matroid just means that you can switch your dessert, switching remove U6 and choose instead U6 prime if it benefits you. So very, very simple. And the good news is for a long time it is known that this is a half approximation. It will give you half approximation like greedy. The bad news is that this is the best possible. So I drew here an instance. This is an instance of set cover. So a set cover, you have one set. This is the element in the submodular function that contain an element y that worth 1. And there is another element here that worth x that you can choose. So if you pick from this partition O1 and you pick from this partition O2, you will get a benefit of 2. But there are two bad sets, bad elements that you can choose. One of them contains x and another small element that worth epsilon. And another one contains just a small element of epsilon. Now, this is the instance. So there is y. You can choose one of the blue sets and one of the green sets. And these are actually the sets. So if you choose this one and this one, you get a benefit of 2. But what happens if you choose this blue and this blue? Now you can see that you don't want to switch this blue for this blue because you will lose 1 plus epsilon and you gain only 1, so you lose money. You also don't want to switch this red for x because x is already covered, so you lose this epsilon. So you are stuck in a local maxima, and this local maxima just worth 1 plus 2 plus epsilon. So this algorithm is not better than half approximation. So what can you do? What can you do is apply some nice and mysterious idea for me, which is non-oblivious local search. What is non-oblivious local search? You apply a local search, but not on your objective, but on a slightly modified objective. And Filmus and Ward showed that there exists such a non-oblivious local search algorithm that will give you 1 minus 1 over E. So the good news is that it's really simple and does not require some sophisticated machinery that I will tell you in 10 minutes. The drawback is that the objective function itself is very complex, and you cannot evaluate it. You need to sample, and then you have still randomization. So what we are doing, we have a deterministic non-oblivious local search. In the limit, it is the same algorithm of Filmus and Ward, but I will not describe it this way. I will describe it in, I think, a simpler way. Great. So here is the algorithm. This is the whole algorithm, the non-oblivious local search, and I will demonstrate it immediately on the partition Matroid. So what is happening here? You are choosing a base, you are choosing elements, but these elements also have colors. These are just fake colors, blue and red, but every dish, you color it blue or you color it red. And now what so the union of these blue and red is just a base. This is the feasible solution that you want to maximize. But what you are trying to maximize is not the objective, which is f of S1 union S2, but you also add here something that depends on the value of just the red dishes and something that depends only on the blue dishes. So this is kind of, you can scale it, so this will be 1 and this will be 2/3 if you like, but this is the whole algorithm. And what can you do in your local search? You can do 2 things. So I will start with 2. One is just to recolor some dish. So you can recolor U6 from red to blue. This will just move it it will stay in the union, so nothing changes, but it will move from the red to the blue, and then you may gain money. So if you can recolor from blue to red or from red to blue, just do it. The other thing is exactly like before. You can switch U6, the dish, with some U6 prime, and then U6 prime, you can color it either blue or red. So what will it do? It will remove U6 from here. It will remove U6 from the union. And then you add U6 prime to the union. And you also add U6 prime either blue or red. This is everything. So you are doing steps like this of recoloring or switching dishes. And that's it until you cannot improve this weird objective function. This is the whole algorithm. Perfect. Now, our real algorithm is just a generalization of these 2 L colors. So you have L colors. You have an objective function that depends, every subset of colors is there with some coefficient that we choose wisely. For the analysis. It only depends on the number of colors, so everything is symmetric. And then, again, you can recolor some dish, or you can remove dish and add another one in any color that you like, and you do it as long as this benefits this objective function. This is the whole algorithm. What can we prove? So this local optimum, if there is 1 color, this is just local search. You can just switch, and this will give you half approximation. Already in 2 colors, what I showed you, this will give you 5/9 approximation. And if you have L colors, it will give you 1 minus 1 plus 1/L to the minus L approximation. If you plug L something like 1/epsilon, you will get this 1 minus 1/E. This is the whole algorithm, right? Simple local search, non-oblivious local search. Great. So I will not prove the performance of this algorithm, although you can prove it in like 2 hours on the board, or it's just a lot of notation, and, but nothing really very difficult. But I will tell you that I cheated a bit, but not too much. So the problem with all local search is that they don't converge too quickly. So they may have a non-polynomial running time. And you should use here the usual solution. Usual solution is start from a good approximation and also make changes as long as there is enough benefit. So these are standard solutions in local search. But actually here we need several more ideas to get really good complexity. And what we show is that we can live with a weaker guarantee, with a relaxed local optimum. And we can get this relaxed local optimum even faster. So to get the real algorithm, the real fast algorithm, we need more ideas. But these are side, I guess. So overall, we have 1 minus 1 over e for monotone functions. Very nice and elegant, I think. Let's move to the part that is less elegant. Yeah, maybe more elegant. So let's move to non-monotone functions. So non-monotone functions are much more difficult, and we understand them much less. So even the approximation ratio, there are questions, and these are really annoying because the question is really easy to state, and we don't know the answer even for cardinality constraint, even if we can choose just k dishes. So after a long sequence of work, our algorithm is the best. It's 0.401, slightly above 40%. And it is known for a long time that you cannot get above 0.478, even for cardinality constant, even if you just need to select k elements. And deterministic algorithms are also behind. And I will tell you in a minute why they are behind. So there are two questions here. What is the best approximation? I don't know the answer. Maybe this one is a good answer. And the other question is randomization is necessary? And I will speak about this here, but I will show you ideas that are used to get these algorithms.
What about the unconstrained case?
So unconstrained, you can get half and optimal, and we have it. Both randomized and deterministic. Yes. So why is it so problematic? Because natural algorithms simply don't work. So I cheated when I said that dessert never hurts. It can hurt you. So for example, local search just doesn't have any guarantee here. So as you all know, chocolate cake is the best dessert. You can see it worth 2 and all other dishes worth 1. But the problem is that it doesn't combine with anything. So while other dishes, if you take S of them, you will gain 1 for each dish. If you take this chocolate cake, it will drop you down back to 2 or even lower. And this is a submodular function. So what happens? Suppose this is a decoy, the chocolate cake, and you decided to take this decoy of chocolate cake because it's worth 2, then you are stuck, because if you take another dish, the value will drop. If you switch, the value will drop. So you are stuck here in a local maxima. You can earn a lot here, but you are stuck with the chocolate cake, which is good, but not enough. And also, at least I don't know how to extend the technique of Filmus and War to non-monotone. Maybe it's possible, but I don't know. I will be happy if this is possible. And the algorithms for this non-monotone case, the best randomized algorithm work in a framework that we call solve fractionally and round, that is used frequently. And I will tell you about these ideas. So what are these ideas? So let's take the linear case. In the linear case where you have an optimization problem, you write it as an integer program. So these are the indicator vectors of your solution, and you want to maximize some linear objective function. What do? You cannot solve the integer program, so you relax it. So you take the feasible region and relax it to the convex hull or some polytope. And then here you get a linear problem, and this is easier. You can solve it and then round, that I will speak in a minute. So you want to do the same for the submodular case. So here you have your integer problem. You have f of x and integer region. So you relax your feasible region to the convex hull or something. But then there is a question of what is the value of a fractional meal? So how to extend the submodular function to fractional solution? So right, you have fractions here. You took half of the chocolate cake, 1/3 of the strawberries, and so on. What is the value? And there are several answers to these questions, and they are quite good in certain problems. But the most useful one for submodular maximization is known as the multilinear extension. So what is the multilinear extension? You simply select each element, each dish, with exactly the probability that the fraction independently, and then you take the expected value of this random set. This is the extension of the submodular function. So you can see that if you have an integer vector, you will get exactly the value. This is why it is an extension. And this is the formula. The probability of selecting exactly S is just multiplying xe of all elements in S and 1 minus xe for all elements that are not in S. So I will tell you some properties of this extension later. Okay, what is solved fractionally and round? There are two steps. One is to find the fractional solution in your polytope that has a large value f of the extension. And then you want to round it to an integral solution and don't lose too much compared to the fractional solution. These are the two steps. I will not speak a lot about the second step, so I will just tell you some ideas. So rounding, there are various ideas here that came up. To round without loss or with very small loss. So for example, in the unconstrained case, you can simply take the elements and get the expected value. So this will give you no loss. But quite surprisingly, you can do it also for Matroids, for general Matroids. I will tell you more at the end of the talk. And you don't need to lose a lot here. So actually here, you don't lose anything. So this is rounding. And the main question in the field, at least for these regions, is how to find a good fractional solution in the Matroid polytope. You should think about partition. So you should select a dessert, but you can select half of the chocolate cake, 1/3 strawberries, and so on, so that the sum is at most 1. So this is the main question that I will address now. Great. So multilinear extension, I will not speak a lot, but it's very useful, and I will tell you just a bit and what I need for this talk. So this is the multilinear extension. Sadly, it's not convex and not concave, but it has nice properties. So first, if the function is monotone, then the derivative of the function is non-negative. This is easy. The second derivative is 0 by some element u because it's multilinear. But the interesting property is that the second derivative by xu and xv for two different elements is non-positive. This is the main place where you use this submodularity property. So this is the main property. And I will need, the only property that you really need for this talk is the following. So suppose you already have fraction x, some fractions, then you can define a subset function that I will call g of s, where you just force the coordinates of s to be 1, and you leave the other coordinates as x. So this is max of xu and yu. And if you define such function, you should believe me, it's not difficult, then g is submodular, and if the function is monotone, then g is also monotone. This is the only, and I'll remind you this function. So actually, there should be maybe a subscript here of x, but I don't put it for simplicity. Great. So let me tell you how people optimize the, give a good fractional solution. And conceptually, the algorithm is quite simple. So you start from a solution that is 0. You have a step size. This algorithm is called measured continuous greedy by Feldman, Naor, and Schwartz, and Roy Schwartz. You take a small step size of 1 over poly n, and then you do 1 over delta iterations. What are you doing in the iterations? You define this function g according to the previous x that you already have. Then you choose a base, which is just the elements that are best independently with respect to g. The marginal is best independently with respect to g. And then you go a small delta step. This is a vector in the direction of these elements. So there is a weird penalty here. This penalty is important, so you won't take the chocolate cake too much. So believe me, this is just, you can think about it as a good direction, a good local direction, and you move just a small delta step towards this direction, and you continue 1 over delta iterations, and that's it. This problem is just a very simple problem. It's just a maximum weighted independent set in a Matroid. This is greedy will give you the solution. And at the end, you just return the final vector. So what they proved is that the final vector, if f is monotone, gives you a 1 minus 1 over e approximation. But even if f is non-monotone, it will give you an approximation of 1 over e, so 36.8%. So this is quite a simple algorithm and quite good. It was the best algorithm for a while. Great. Where is the randomness? Right? You don't see the randomness because I cheated a bit, because I didn't tell you everything that you need. So the randomness is hiding somewhere, and it hides exactly here. So evaluating G requires evaluating the multilinear extension. And this multilinear extension, if you remember, may have all subsets, all 2 to the n subsets. So you need a 2 to the n value oracle calls. If you use 2 to the n value oracle calls, you can just solve the problem. So you don't want this. So here in the evaluation of G, you just sample the multilinear and use Chernoff and use some accuracy. And this is, it is shown that this is enough. Then you will get a randomized algorithm and quite a slow one. So this is where the randomization. Great. So here is the solution to avoid randomization. So if you like the extension, the multilinear extension, it looks like this. You probably like the extended extension that looks like this. So what is the extended extension? Instead of having a vector of size n, you have a vector of size 2 to the n, and you have a coordinate for each subset of elements. And then you do the same. You choose each subset independently, with the probability ys. And then the value of this extended extension is just the value of the union, the random set that is the union of everything that is there. So this is the extended extension. So just for intuition, if you take ys just the singleton sets that contain a single element, you will get exactly the extension because you choose a set that contains only one element and you choose it independently. So this extends the extension. And also what you can see is that if you choose a vector es that just has 1 in the coordinate of some subset, you will get exactly the subset itself. Or if you take several indicator vectors, you will get the union. So it is an extension, but an extended extension. So right now, just a definition. And as you can expect, it behaves more or less like the extension, the standard extension. So this is the standard extension. Vectors x are of size n. Extended extension, the vectors are of size 2 to the n. And the properties are quite similar. If f is monotone, the derivative is only increasing. These are easy properties that you can prove. It's multilinear, so the second derivative is 0. The submodularity is true, but only if you take two coordinates that are disjoint. So if you take, for example, two sets that contain one element and another element, this will be true. So this is going to be non-positive. This is the main property of submodularity. And the same property, if you take G, if you have a vector y, and you define a function S that force you to take some elements or some subset, you will get a submodular function and even monotone if f is monotone. So basically, the properties are quite the same, it's just that it's 2 to the n. Great. Now I want to extend the solve fractionally and round. So what do I mean by solve fractionally and round? I need another definition, a natural one. So for each element u, I can define the marginal probability of u by y, which is just the probability that u is in this union when you pick each set separately, independently with probability ys. So the marginal vector is now a vector of size n. This is, you should think about it still as fractional vector, not as probability. What is solved fractionally and round? You're looking for y of a vector of size 2 to the n, such that the marginal, the fractional is in P, is feasible in your region. It has a large f of y, the extended extension, and then you want to round this y to a real subset and don't lose too much. Right? So the main thing is that you want your marginal to be okay. Great. Oh, I have not too much time. Now, what is the problem? I told you that in order to evaluate the multilinear extension, you need 2 to the n value oracle. To evaluate the extended extension, you may need to evaluate 2 to the 2 to the n. So this is really even worse. But here is the solution and the whole idea. The whole idea is that if you don't have too many fractional coordinates in your vector, so frac is the number of coordinates that are strictly between 0 and 1. It's almost the support. It doesn't contain 1. Then, right, what do you need in order to evaluate this? All the 1s you are taking to your sets, all the 0 you can drop, and then you are left with just 2 to the fractional of y. So if you could construct vectors that are extremely sparse, this can still be done in polynomial time. So the idea is to construct extremely sparse vectors y. Here is the algorithm. So this is the measured algorithm that I showed you before. This is our algorithm. Let's observe the differences. So first, we had here polynomial number of iterations. Here, think about epsilon as a constant. Here you just have 1 over epsilon cube iterations. So you don't have a lot of iterations. You just move in some constant step size. This is the idea. Here is the main difference. So here, if you recall, we chose the elements, the subset of elements that are most profitable right now with respect to this xi minus 1. Here, what we are able to do, we define the same g with respect to yi minus 1, but we are able to choose not R elements. Think about R as large. We choose just big boxes. You can think about 1 over epsilon boxes. It's a constant number of boxes that already give you a good guarantee. So the guarantee that we need to prove that this algorithm is good is that the sum of marginal contributions separately is at least the value of the optimal solution, the value of the optimal solution, the contribution of the optimal solution. We are able to do it with very small number of boxes that contain many elements. So T1 to T1 over epsilon are boxes that contain separate elements. The union is a base. And then we are able to prove that the sum of the marginal contribution of these is at least is very similar to the guarantee that you get from R elements. And this is enough to prove everything. And then the punchline. So the punchline here, right, the number of coordinates that are non-zero grow by R. So every time you grow by R and this rapidly grow to n, and then you need to evaluate it. You need a lot of queries. But here, in the extended extension, the number of coordinates that grow is just 1 over epsilon. You have 1 over epsilon cube iteration. So overall, you have a very sparse vector of at most 1 over epsilon to the 4th. This is it. Now, this split is maybe the main, but it's really simple. So I will skip it because I don't have a lot of time, but split is just a greedy. You pick boxes, and you throw elements that keep you feasible, and you throw an element which maximize the profit. So this is just greedy, and you can implement it even faster with some additional ideas. Okay. So overall, what we get is almost the guarantee of up to epsilon, the guarantee of what the previous algorithm get, but with a very sparse vector that contain large sets, large boxes. And now, what I will not tell you about is how to round this solution. So rounding is a different issue. But I will just tell you that we have a lemma that if you take a vector y, the marginal vector, if you take the standard extension, it will give you more value. So you can use any rounding for the standard multilinear extension, but this will be randomized. And you can even do it faster. Let's skip this. What we do in order to do it deterministically is we extend something called pipage rounding that was used in the standard extension, but we need to be very careful here. We cannot really change coordinates that combine a lot of sets, so we need more ideas. And most importantly, we need to keep that the number of fractional coordinates is very small, since otherwise we cannot evaluate the function deterministically. So we need to be very careful, but these are all solvable problems. Great. So let's have a conclusion. So we had this algorithm which is deterministic that gives you almost the guarantee of a previous good algorithm for monotonicity. We can have even a randomized algorithm, which is even slightly faster than the previous local search algorithm. So even here we have, with certain rank, we get faster algorithms. And the most important takeaway is to work with large boxes. So throw several elements together and don't work with individual elements, but with large boxes that contain a lot of elements. Great. So there are plenty of open problems here. So first, you can try to de-randomize this best algorithm that is probably not the best algorithm there is. We think it is possible, but it's a lot of work. There are lots of components there. You can de-randomize the other algorithms that were used, try to use this technique to de-randomize. The most important question, in my opinion, is the following that I hid quite good. Our deterministic algorithms are actually efficient p-tas. So what is the dependency on epsilon? So think about the colors. If you have 1 over epsilon colors, you have 2 to the 1 over epsilon subset that you need to evaluate. The other algorithm also has dependency even worse, exponential. So can we get a real p-tas for these questions? Maybe yes, maybe not. I'm not sure what is the answer. So, thanks.
Thank you so much for this very nice talk. Any questions?
Everything is so clear. Yes.
I was wondering, yeah, I don't know whether it's a good question or not, but whether you could explain the idea behind, in the first part of your talk, where you get local search unstuck from those bad local optimal solutions. What is the idea? Is there some intuition behind?
Why it is working?
Why is it working?
So I will need another half an hour to explain. But basically, you analyze this local optimum, and you get huge equations that with this alpha, and you use submodularity because subset for a subset with some colors, you also have the coefficients here of all subsets of the subset of different colors. And this will give you, you can use submodularity to bound it, and then you get a telescopic sum with all this objective, and it gives you a recursive formula for choosing the right alpha j there that you can scale. And this will give you the solution. So I taught an advanced course, and I actually proved this 5/9. It took me an hour on the board, more than an hour and a half. But nothing that I will say fancy. It uses just basic submodularity inequalities, and the proof is quite elegant, except for the notation that is not so easy with these subsets.
More questions?
Submodular is easy.
So surprisingly, randomization does not help in for the first problem.
So the question that people ask is, why do we care about randomization?
Yeah, or when does it help, right? I mean, so.
Yes. So right. Is it why are we interested in deterministic algorithm? So first, it is not clear that there is randomization in nature. I'm not sure, at least. But somehow it gives me at least deterministic algorithm that I understand the problem better somehow. Yeah, so, and it's good. So there are excuses that I give in courses of why you want deterministic. If you don't want that if you press on brakes and randomization with probability 1/1,000,000, it will not work. Or yeah, so for me, at least this algorithm is very elegant and give you understanding of what is going on with at least with the monotone submodular functions.
Okay,
Thank
any more
you.
questions? If not, then let's thank Niv again.